Section 4.2 talks about exponential functions. So what I have here, guys, is I have an example of a linear function and an example of an exponential function. So here we have our x values, 0, 1, 2, 3, 4, 5, and we have our y values. So if you notice, from 3 we're going to 5, we're adding 2. From 5 we're going to 7, we're adding 2. So each step that we move in the x direction, we add 2 to our y value. So an exponential function, if you notice 0, 1, 2, 3, 4, 5, from 3 we're going to 6. We doubled it. From 6 we went to 12. It was doubled again. It's doubled, it's doubled, it's doubled. So that's the difference between a linear function and an exponential function. A linear function goes up by the same amount. So we're either adding a certain number or we're subtracting a certain number. Exponential functions are, it's multiplied by something, okay? So, excuse me, we have a definition here, and it says a function f represented by f of x equals c times a to the power x, where a is positive, that's all this means. A is greater than 0 means a is positive, but it's not equal to 1, and the number c is also positive. This is what we call an exponential function. So it says, for the first example, for f of x is equal to 2 to the power x, find each of the following. We're going to look for f of 1. So remember, all I'm going to do here is I'm going to come back and 2 to the power 1. Well, 2 to the power 1 is just 2. Okay. 2 squared. Well, 2 squared is 4. 2 to the power negative 1, remember, this is 1 over 2, because of our negative exponent. And 2 to the power negative 2 is the same as 1 over 2 squared, which is 1/4. Okay. So let me move on to the next one here. We'll go about it exactly the same way. So it says f of x is equal to 1/5 to the power x. Find f of 1. Okay, so f of 1 is going to be 1/5 to the power of 1, which is still 1/5. 1/5 to the power of 2. So remember, 1 squared is 1, 5 squared is 25. Okay. 1/5 to the power of negative 1. Remember, I'm going to take the reciprocal of this. 5 over 1 to the power of positive 1, which is just 5. And then 1/5 to the power negative 2. Okay. I'm going to take the reciprocal of this piece, which is 5 over 1. I'm going to square it. It would just be 25, right? Okay. So, a little bit about exponential functions. It says because the graph of f of x equals a to the power x is that of a one-to-one function, to solve a to the power x1 equals a to the power x2, we only need to show that x1 is equal to x2. So this is how we solve exponential equations, which is an equation where the variable appears as an exponent. That's what we have right here. Okay, so I'm going to rewrite this. This says 4 to the power x is equal to 2. But I'm going to rewrite 4 as 2 squared to the power x equals, and I'm going to think of this 2 as 2 to the power 1. Okay. Now, according to my rules of exponents, we can multiply exponents together. So that's going to be 2 to the power 2x equals 2 to the power 1. Since our base numbers are the same, that means that my exponents will also be the same. So that's telling me that 2x is going to be equal to 1. So when we divide both sides by 2, x is going to be 1/2. Okay. Let's see if we can solve the next one here. I'm going to try to go about it the same way. Okay. So here I have 5 over 2 to the power x equals, I'm going to try to rewrite this part. And I want to rewrite it so that I see 5s and 2s in there, okay? So how about if I think about this as 2 over 5 squared, okay? Now, my base numbers aren't exactly the same. This is 5 over 2, this is 2 over 5. But We could make them the same. If I take the reciprocal here, 5 over 2, that means I'm introducing a negative exponent. My negative exponent is negative 1, but because this is being squared, it becomes a negative 2. So now, since my base numbers are the same, then my exponents are going to be the same. So in this case, x is equal to negative 2. Okay. All right, let's keep going here. I'm going to try to do the same thing. So I have 2 to the power 3 minus 2x equals, I'm going to think of 8 as a power of 2. I know that's 2 to the third. So that means that since these base numbers are the same, my exponents are also going to be the same. So 3 minus 2x is equal to 3. So I'm going to go minus 3 and minus 3. That's going to be negative 2x equals 0. So when I divide both sides by negative 2, I end up with x is equal to 0. Okay. All right, let's see if we can do the next one the same way. So I notice I have 27 and 9. Those are both powers of 3. So I'm going to write them as powers of 3. So 27 is 3 to the third power. Okay, and this is a 4x right here. And 9 is 3 squared. And this is an x plus 1 right here. Okay, so now I'm going to go ahead and multiply my exponents. So this is going to be 3 times 4x is 12x equals, I got to multiply that 2 times everything there. So 2x plus 2. And again, since my bases are the same, then my exponents are going to be the same. So this is 12x equals 2x plus 2. Minus 2x on both sides. This is going to leave me with 10x is equal to 2. So when I divide both sides by 10, we're coming up with x is equal to 1 over 5. The next part of 4.2 is compound interest. It says if P dollars are deposited into an account at an annual rate of interest of R, compounded, which means paid n times per year, then after T years, the account will contain A dollars according to the following formula. Okay, so here's my compound interest formula. All right, so let's just make sure we understand what each of these variables stand for. P is the principal. That's the amount of money that we're investing, okay? We're putting in the bank. N, the number of times compounded in a year. T is the number of years. And R is our interest rate. Okay? So let's take a look and see if we can figure this problem out. So it says, suppose $1,000 is deposited into an account paying 4% interest, compounded per year quarterly, 4 times a year. All right, find the amount in the account after 10 years with no withdrawals. Okay, so the amount of money we're investing is 1,000. My interest rate is 4% as a decimal, that's 0.04. If it's being compounded quarterly, that is 4 times a year. Okay. And T, we're looking here for 10 years. Okay. So I'm going to go ahead and write down my formula, P times 1 plus R over N to the power NT. Okay. All right, so now I'm going to write down 1,000 times 1 plus 0.04 over 4, that's my N, to the power N times T. So 4 times 10 is 40. Okay. So let's see if we can figure this part out. I'm going to grab my calculator, move it over here real quick. Actually, I'll leave it right here. I'm going to show you guys that when you're doing this, this is a straight plug and chug problem. I'm going to write out exactly what I see in my screen. So I'm going to put 1,000. And then I see parentheses, so I'm going to write them down. 1 plus 0.04. What are we doing next? We're dividing it by 4. What do we have after that? close those parentheses. What do we have after that? Raise it to the power of 40. Okay. I'm going to hit enter, and I'm coming up with, since this is money, I'm going to go to 2 decimal places, 1488 and 86 cents. So 1488 and 86 cents, right? And here's my answer for part A. Now there is a part B to the question. Part B says, how much interest is earned over the 10-year period? Remember how much money, so we ended up with 1488 and 86 cents, right? But we started off with $1,000. So the interest that we earned was $488.86. That was my interest. Okay. All right. The next problem, we're going to do the same type of thing. It says use the compound interest formula to approximate the final value of the amount. Okay, so again, let's start off with a couple of pieces. The principal, $950. Okay. My interest rate, 3% is 0.03. And if it's being compounded daily, we're going to use 365 days in a year. And T, the number of years, is 20 years, okay? So now I'm going to write down my formula. Okay. So let's start doing a little plug and chug here. P is 950, so I'm going to write 950 times 1 plus 0.03 divided by, since it's daily, it's 365 to the power, I need to multiply these two numbers together. So let me take my calculator. What's 365 times 20? I don't know, big number, 7,300. Okay. So now, like I said before, I'm going to type this in exactly as I see it. I see 9,500, or 950, I'm sorry. Parentheses, 1 plus 0.03 divided by 365 raised to the power 7,300. And I'm going to hit enter. And if you notice what I'm coming up with, again, I'm coming up with 1730 and 97 cents. So 1730 and 97 cents. And that's how much money we'll have after 20 years. Okay. Now, we have something called continuous compounding. Continuous compounding is the idea that the money is always being compounded. So when we did the problem over here the first time, let's see, where were we? Right here. It was being compounded quarterly, which was 4 times a year. This one is being compounded daily, which was once a day. Continuous compound means it's always being compounded, okay? They're always calculating that interest. So it says if P dollars are deposited at a rate of interest R compounded continuously for 2 years, then the amount, compound amount A in dollars is given by this formula right here. Okay, so guys, just a heads up, this number E is an irrational number. Its E is approximately 2.71828. It's one of these kind of like a square root of 3 type number. It's irrational. And it comes up pretty often in application problems. So I'm going to show you how we're going to do this on our calculator again. Okay, first thing, P is 5,000, right? Deposit in the account paying 3% interest. So my interest rate is 0.03. Compounded continuously, so it just means I'm going to use this formula here. And my time is 5 years. So this is what my formula looks like, the PERT formula. So our P is 5,000. Okay. E to the power 0.03 times 5. Like I said, this is going to be a straight calculator type problem. So let me clear my screen, okay, and move it over a little bit. First thing I see is 5,000, so let's write that down. Okay, times. Now, when I want to get to my E, I want you to look at the number 4 and look at directly to the left of it. Do you see there's a button that says LN? And right above the LN, there's a little E right there. I need to get to that E. The way I do that is I'm going to hit second. I'm going to hit my LN button. And if you notice, there's my E. It automatically opened up my parentheses for me. If it didn't open up parentheses for you on yours, just type in an open parenthesis. What am I going to type in on the inside? 0.03 times 5. Close those parentheses up, hit enter, and I'm coming up with 5809 and 17 cents. 5809 and 17 cents. And there is my interest, okay, or my amount in the bank. Okay, so let's take a look at this next one. It says Becky must pay a lump sum of $6,000 in 5 years. What amount deposited today, the present value at 3.1% compounded annually, will grow into $6,000? Okay, so hold on real quick. Okay, so in this problem here, let's go ahead and start writing in the amounts that we know. Now, it says that she has to pay $6,000 in 5 years. So the amount that she's going to need is actually going to be $6,000. We don't know the principal because that's how much we're trying to figure out, what amount deposited today, the present value. Okay. We do know that the interest rate is 3.1%, which is 0.031. We know that our n, if it's being compounded annually, is just once a year, and our time is 5 years, so t equals 5. So when I write out my formula, a equals p times 1 plus r over n to the power nt, we actually know the amount. We know the amount is 6,000. Okay, it's equal to p 1 plus 0.031 over 1 to the power n times t. 1 times 5 is still 5. So this is going to be 6,000 equals p 1 plus 0.031 to the power of 5. Okay, so we're almost there. 6,000 equals, I can add these together, 1.031 to the power of 5. Now, I'm trying to solve for the letter P, right? That's the letter we're trying to solve for. So let's divide by 1.031 to the power of 5 on both sides. Okay. And I'm going to do this on my calculator. So I'm going to take exactly what I see. 6,000 divided by parentheses 1.031 to the power of 5. Hit enter. And so today we have to deposit $51.50 and 60 cents. $51.60 and 60 cents. There we go. This is the amount that we have to deposit today. Okay. So along with interest problems, some of the other applications of exponentials are called the population growth model right here. Okay, so here's my population growth model. And it says f of x equals a times 1 plus r to the power t. A stands for the initial population. R is the growth factor. So the first problem here says deer population. The exponential growth of a deer population in Massachusetts can be approximated using this formula, where 50,000 is the initial deer population, 0.06 is the rate of growth. F of x is the total population after x years have passed. So x is the number of years. Find each value to the nearest 1,000. So it says predict the population after 4 years. Okay, so for part A, we're just looking for f of 4. Okay, that's going to be 50,000, 1 plus 0.06 to the power 4. So again, I'm going to do this on my calculator, and I'm going to type in exactly what I see. 50,000 times parentheses 1 plus 0.06, close that off, raised to the power of 4, hit enter, and I'm coming up with 63,123. 63,123. Now it is asking me to round to the nearest 1,000. So to the nearest 1,000, it would be 63,000, right? Because that number is not 5 or more. So the nearest 1,000 would be 63,000, okay? Now, part B says, if the initial population was 30,000 and the growth rate was 0.12, how many deer would be present after 3 years? So remember, I'm using this, I'm using this formula right here, okay? And sorry about that, guys. This should have been an x, not a t. But the idea is the same. Okay, so f of x equals a. Let me just write it down. F of x equals a 1 plus r to the power of x. Okay, so now they're telling me that the initial population was 30,000. Okay, so I'm going to say f of x equals 30,000. 1 plus my growth rate factor is 0.12 to the power of x, and we're going to look for the population after 3 years. So again, I'm going to type in exactly what I see on my calculator. So I'm going to type in 30,000, 1, 2, 3, times parentheses 1 plus 0.12, close that off, raised to the power of 3. Okay, and here I'm coming up with 42,147. So 42,147. Okay, again, it says to round to the nearest thousand. So that the nearest thousand, this would have been 42,000, right? Okay. Now, part C says, how many additional deer can we expect in 5 years if the initial population is 45,000 and the current growth rate is 0.08? Okay, so initial population 45,000, growth rate is 0.08. So 46, or f of x, I'm sorry, this is my basic formula. So A is 45,000. 1 plus R is 0.08 to the power x, and we're looking for 5 years. Okay. So again, let's type this in exactly as we see it. 45,000 times parentheses 1 plus 0.08 raised to the power of 5, and I'm coming up with 66,119, but to the nearest thousand would be about 66,000. Okay, this is what I'm coming up with. Now I want you to read the question though. How many additional deer can we expect in 5 years if the population is 45,000? So what does that mean? That means that right now we have 45,000. 5 years later, we're going to have 66,000. How many additional deer did we expect and did we gain in those period of 5 years? Well, we're going to take 66,000 minus 45,000, and that's going to give me 21,000, right? So that's really my answer that I'm looking at there. And that right there was 4.2.